All right, welcome back, everybody. This is 3.2, part 2. There was an issue with my mic, so I had to pause the video and pick back up where I left off. So I'm on page 120, looking at the top of this page in my ebook where it says molar mass. And as you may remember from your first year chem class, molar mass is the mass of 1 mole of an element's atoms. That's what its name implies, the mass of 1 mole of an element's atoms. Book goes on to say that molar mass of an element is its atomic mass expressed in grams. It's atomic mass expressed in grams. So I'm going to take us to a periodic table to remind us about what an atomic mass is and how from an atomic mass we can determine an element's molar mass. So we're looking at a periodic table, of course, and I'm focusing on the element boron here. I want to remind everybody that the number above the symbol is the atomic number, and that is what defines that element, and it's the number of protons in the nucleus. The number of protons of the atomic number defines the element. The decimal number, typically written underneath the symbol, is the atomic mass of that element. That's the mass in atomic mass units, in AMUs, of an average atom of boron. And the reason it's a decimal number is that boron has several isotopes. Some boron has 5 protons and 5 neutrons, and all those boron atoms would weigh 10 AMU, with each proton and each neutron being 1 AMU. An isotope of boron with 5 neutrons would weigh 10 AMU. But some boron atoms, in fact, about 80% of them, have 6 neutrons, and those weigh 11. So if you take the weighted average of all the isotopes of boron, all the different versions of boron with different numbers of neutrons, and account for their percent abundance in nature, we get the atomic mass of the element, which is that decimal number. And in boron's case, it's 10.81 AMUs. Well, if you've got a mole of boron atoms, right, then it turns out, because Avogadro's number, a mole, is actually how many AMUs there are in a gram. If you have a mole of boron atoms, it weighs 10.81 grams. The molar mass of boron is 10.81 grams. And I'd really like us to be in the habit of referring to molar mass in grams per mole. So we should say boron's molar mass is 10.81 grams per mole. Carbon's molar mass, to the right of boron, is 12.01 grams per mole. So the atomic masses, these decimal numbers underneath the elements, to us really are the molar masses, because that's a far more useful value to refer to than the atomic mass. For compounds, like water or sodium chloride, for compounds that could either be ionic or molecular, it is the sum of the element's molar masses that is that compound's overall molar mass. Our book uses the terms molecular mass or formula mass for if a substance is molecular versus ionic. We're just going to all call them molar masses. Whether it's an ionic compound or molecular, we're going to refer to their molar masses as just molar masses. So in water's case, with the formula H2O, if you add the mass of oxygen, 1 oxygen to 2 hydrogens, it would be 18 AMUs. Or the molar mass of water, the mass of 1 mole of water, would be 18 grams per mole. In sodium chloride's case, its formula being NaCl, the sum of the atomic masses of sodium and chlorine is 58.5 AMU, so the molar mass of sodium chloride is 58.5 grams per mole. And as we look at the bottom here, our book says that the molar mass of a substance is its atomic, molecular, or formula mass expressed in grams. All right, so I've just flipped my page. I'm now at the top of page 121 in my ebook, and I'm looking at practice problem 1. It says, what is the molecular mass of nitrogen dioxide? To us, that's what is the molar mass of nitrogen dioxide. Well, nitrogen dioxide is a molecular compound. Its name suggests there's 1 nitrogen atom and 2 oxygen atoms. So its formula is going to be NO2. NO2. To find the molar mass of nitrogen dioxide, I need to know what the molar mass of nitrogen is. It's 14.01. I'm going to wait to write grams per mole until the end. Normally I like to put units in my work, but for molar masses it's fine to put at the end. And then there's 2 oxygens that each weigh 16.00 grams per mole. 2 times 16 is 32, 42, 46.01 is the sum of those numbers. The molar mass of nitrogen dioxide is 46.01 grams per mole. Memorizing some of the more common elements' molar masses is helpful. That way you don't have to keep looking them up in your book, and it's something that we regularly do, is find the molar masses of substances. So I'm back on that same page on my ebook, page 121, and I'm looking at this little section here. Like before, with Avogadro's number, we see that molar mass has an equivalence. The difference, though, is that for a mole of any substance is always 6.02 times 10 to the 23. That's a fixed number no matter what type of substance. But for molar mass, it varies because the molar mass of every atom or every different compound is going to be different. That's why we got a question mark there. So the molar mass will vary for every element or for every substance. We have two conversion factors that we can use for many equivalents, with 1 mole on the bottom and the molar mass in grams on the top, or with 1 mole on top and the molar mass in grams on the bottom. This is how we'd normally express molar mass, is grams per mole, but it can be expressed as its reciprocal, which is moles per gram as well. Any fraction can be flipped over and mean the same thing. All right, so I'm still on this same page, looking at practice problem 2 on page 121 of my ebook. Looks like I'm converting from moles to grams. I got 0.87 moles of NH3. That's ammonia, by the way, and I need to find the mass. So I'm going to be using the molar mass. All right. NH3 has 1 N in it. Each nitrogen weighs 17.01 grams per mole. There's 3 hydrogens, each weighing 1.01 grams per mole, and the sum of those numbers is 17.04 grams per mole. So I've got my molar mass. I now need to write that in my DA box. Well, I can either write 17.04 grams over 1 mole, or I can write 1 mole over 17.04 grams. Again, it's all about unit cancellation. I need moles to cancel, so I put 1 mole on the bottom, and I put 17.04 grams on the top. And to be, again, really clear, it's ammonia. Yes, only ammonia is involved in the problem, but soon that won't be the case. I'm going to put the formulas there as well. Moles cancels. I'm left with grams. And the final answer, unrounded, is 14.82. But with 0.87 having only 2 significant figures, that's going to round to 15 grams of ammonia. So I'm going to flip the page. I'm now on 122 of my ebook. I'm going to solve practice problem 2 with you. We've got 3.88 grams of CO2. We want to convert it to moles. I've written 3.88 grams of CO2 in the upper left-hand corner of my DA box. I've already calculated the molar mass of CO2, which is 44.01 grams per mole, 1 carbon, 2 oxygens. And again, I could either write 44.01 grams over 1 mole, or I could write 1 mole over 44.01 grams. Because I'm starting with grams and I need grams to cancel, I put the 44.01 grams on the bottom, I put the 1 mole on the top, and my final answer, 0.08816. With just 3 significant figures, I'm going to get 0.088, and that 6 is going to round the 1 up to a 2 moles of CO2. This one, by the way, is exact. It has an infinite number of significant figures. It'll never restrict sig figs, because what we say is in exactly 1 mole of CO2, there's approximately 44.01 grams. So there's some uncertainty in that number. That number is exact. That's it, folks. This is part 2 of lecture 3.2. Look forward to seeing you for 3.3.